At this scale of exposure, nothing organic should remain stable for long, and yet it does. An animal exists whose survival depends on forcing thousands of liters of surrounding water directly through its own body, without discrimination, without pause, without the ability to say no. Every second alive is another second spent ingesting whatever the ocean carries: bacteria, viruses, microplastics, heavy metals, chemical runoff, everything suspended between clarity and poison. Logic suggests this should end quickly. Instead, oysters persist. They do not hunt, they do not flee, they do not choose safer conditions. They anchor themselves in place and open their bodies to the environment in the most literal way possible. Water enters, is processed, and leaves cleaner than before, not because the oyster intends to clean anything, but because filtration is the only way it can breathe and feed. The paradox appears immediately. The very act that keeps this animal alive is the act that should overwhelm it. An adult oyster can filter tens of gallons of water per day, pulling oxygen and microscopic food particles from the flow, while also accumulating pathogens and toxins at concentrations far higher than the surrounding water. There is no protective barrier that separates nourishment from danger. The gills that capture algae also capture industrial residue. The tissues that sustain growth quietly store substances the oyster cannot metabolize or remove. From a biological perspective, this is a body operating without a safety margin. Most animals rely on selective intake, behavioral avoidance, or mobility to reduce exposure. Oysters have none of these options. They solve survival by committing fully to exposure, accepting every risk simultaneously. The system works only because the oyster's metabolism is slow, its demands minimal, its expectations almost non-existent. It grows incrementally, shell by shell, layer by layer, while its soft tissues tolerate conditions that would kill faster, more complex organisms outright. There is no brain to register danger, no stress response to escalate, no decision-making process that could interrupt the flow. The oyster continues filtering even when conditions degrade, even when pollution spikes, even when oxygen levels fall, because stopping is not an option built into its biology. This is not resilience in the heroic sense. It is endurance born from limitation. The oyster does not resist the ocean. It yields completely, trusting that the math will work out over time. And disturbingly, for long periods, it does. Entire coastal systems rely on this quiet transaction. As oysters feed, suspended particles are removed from the water column, increasing clarity, stabilizing nutrient cycles, and indirectly supporting seagrasses and other marine life. The cleaner water is not a gift. It is a side effect of an organism pushing its own tolerance to the edge continuously. Each oyster functions as a living intake valve, processing the environment with its own body as the filter medium. No replacement parts, no purge cycle, just accumulation. From the outside, an oyster reef looks inert, almost geological. But internally, millions of soft bodies are engaged in the same risky exchange, drawing the ocean inward, altering it slightly, while being altered in return. This arrangement should collapse under contamination alone. Historically, it often has. But where oysters remain, they demonstrate an unsettling truth about biological systems. Survival does not always require protection. Sometimes it requires exposure so complete that the organism becomes inseparable from the threat itself. The oyster does not conquer its environment, and it does not adapt away from danger. It survives by becoming a functional component of the hazard, filtering it, storing it, and enduring it, until it can't. For most animals, feeding is a controlled interaction with the environment, limited in duration and selective by design. For oysters, feeding is an unbroken physiological state that never truly turns off. The gills do not switch roles between breathing and eating. They perform both simultaneously, continuously, drawing in water whether conditions are favorable or lethal. This creates a biological contradiction. The oyster must maximize intake to survive, yet every increase in intake amplifies the internal concentration of whatever the water contains. At sufficient scale, this should produce systemic failure. It rarely does, at least not immediately. An oyster feeds by trapping microscopic algae and organic particles in mucus-lined gill structures, transporting them toward the mouth with cilia. The process is slow, passive, and relentless. There is no sensory system capable of evaluating whether the incoming material is nutritious, toxic, or pathogenic. In polluted waters, this means heavy metals like mercury and cadmium accumulate in tissues alongside food. Pathogens concentrate as well, often reaching levels many times higher than in the surrounding water. From an energetic standpoint, this is a terrible trade. The oyster expends energy filtering water that may offer little usable nutrition while increasing its internal toxic load. There is no adaptive switch to reduce feeding when returns diminish. The system is locked in. This is where the biological limit becomes visible. Oysters survive not because this strategy is efficient, but because their energy requirements are extraordinarily low. Growth is slow. Movement is non-existent. Repair happens at a pace that would be fatal for animals with higher metabolic demands. When conditions worsen, oysters can partially close their shells, reducing intake, but this response is temporary and costly. Closed shells mean reduced oxygen, rising internal acidity, and eventual suffocation if maintained too long. The animal faces a forced choice between two failures: filter and poison the body, or stop and starve. Neither option is sustainable indefinitely. The unsettling part is how long oysters can remain suspended between these outcomes. Weeks, sometimes months, of marginal conditions are tolerated through metabolic suppression. The heart rate slows, energy consumption drops. The oyster waits, not in a strategic sense, but because waiting is the only state available. During this time, feeding never truly ceases. Even minimal shell opening allows some exchange, some intake, some accumulation. This creates a delayed cost structure. Damage does not appear immediately. It compounds quietly. Toxins bind to tissues. Pathogens persist in low-level infections. The oyster remains alive, filtering, contributing to water clarity, even as its internal condition degrades. This lag between cause and effect is what allows the system to function at all. If the consequences of feeding were immediate, oysters would not exist as a species. Instead, harm is deferred, stretched across time, often long enough for reproduction to occur. From an evolutionary perspective, this is sufficient. From a systems perspective, it is deeply unstable. The oyster's feeding strategy works only because failure is postponed, not prevented. When collapse finally arrives, it appears sudden, often triggered by a minor additional stressor, a temperature spike, a drop in oxygen, a brief pollution event. The body had no buffer left. The feeding that sustained life becomes indistinguishable from the process that ends it. And the surrounding water may still appear clean, improved even. At the exact moment the organism filtering it crosses an internal threshold, it can no longer survive. Stability in ecosystems is usually associated with redundancy, resilience, and tolerance to variation. Oyster-based systems violate that expectation. Vast stretches of coastline, entire food webs, and critical nutrient cycles are anchored to organisms that operate within a remarkably narrow band of survivable conditions. A slight shift in temperature, a modest drop in oxygen, a brief change in salinity, any one of these can push oysters beyond physiological tolerance. This creates an uncomfortable contradiction. The more important oysters become to an ecosystem, the more fragile that ecosystem actually is. Oyster reefs improve water clarity, stabilize sediments, and create complex three-dimensional habitats used by fish, crabs, and invertebrates. They reduce excess nutrients by removing phytoplankton from the water column, indirectly preventing algal blooms that can deplete oxygen. Yet the oysters performing these functions are themselves among the first organisms to die when environmental conditions deteriorate. Their tolerance limits are not generous. Warmer water increases metabolic demand while simultaneously reducing dissolved oxygen. Acidification interferes with shell formation. Freshwater runoff alters salinity beyond optimal ranges. None of these stressors need to be extreme. They only need to persist. Mortality events often occur not during dramatic disasters, but during periods of mild but sustained deviation from normal conditions. From a systems perspective, this is dangerous design. There is no durable backbone species capable of absorbing shocks. Instead, the system relies on continuous survival of organisms that cannot retreat, relocate, or rapidly adapt. When oyster populations decline, the effects cascade outward. Water becomes cloudier, light penetration drops, seagrasses weaken or disappear, sediments resuspend, further degrading water quality. Nutrient cycling shifts towards states that favor harmful algal blooms. The very conditions that oysters once moderated now intensify, accelerating further loss. What makes this unsettling is the lack of warning. Oyster reefs can appear stable until they are not. The organisms do not exhibit obvious distress signals visible at the ecosystem level. Filtration rates decline gradually. Reproductive output drops quietly. Then a threshold is crossed. Mass mortality follows, often within days. The ecosystem loses its filtration capacity almost overnight. There is no backup system waiting to engage. Other filter feeders cannot scale quickly enough to replace the loss. Recovery, if it occurs at all, takes decades. This fragility would be easier to accept if oysters were rare or peripheral. They are not. Historically, they dominated coastal systems, forming reefs so extensive they were navigational hazards. Human exploitation reduced those populations dramatically, but even remnant reefs continue to play outsized roles. This means modern coastal environments are often functioning at the edge of failure, propped up by sparse populations of organisms already operating near their biological limits. The unsettling realization is that ecosystem stability here is an illusion created by ongoing biological strain. The system does not persist because it is robust. It persists because failure has not yet propagated far enough. Oysters hold the line not through strength, but through constant, quiet attrition, absorbing stress until their own tolerance is exhausted. When they finally give way, the ecosystem does not slowly degrade. It falls into a different state entirely, one that is harder, sometimes impossible, to reverse. What appears solid in an oyster reef is not alive. The structure that resists waves, redirects currents, and shelters countless organisms is built almost entirely from accumulated shells, the mineral remains of individuals that did not survive. Living oysters occupy only the surface layer. Everything beneath them is a record of failure preserved as calcium carbonate. This is the next contradiction. The stability of the system depends on continuous mortality. Oysters grow by extracting calcium and carbonate ions from the water to form shells, a process that already operates near chemical limits in marine environments. When an oyster dies, its shell does not disappear. It becomes substrate, elevating the reef, creating attachment points for larvae, and maintaining the structure above shifting sediments. Without this buildup of dead material, oyster reefs flatten, disperse, and eventually vanish. In other words, survival at the population level requires a steady supply of bodies. This is not an accident of history. It is a structural necessity. Each generation inherits a foundation built from the physical remnants of previous ones. The living cannot construct the reef fast enough on their own. They rely on time, accumulation, and loss. From a biological perspective, this arrangement is inefficient and risky. Shell formation is energetically expensive. It becomes more difficult as waters acidify, because lower pH reduces the availability of carbonate ions needed for calcification. When shells dissolve faster than they accumulate, the reef erodes from within. The architecture collapses not because the living oysters fail to attach, but because the dead no longer persist. This exposes another limit. Oyster reefs are not maintained by active repair. There is no organism tasked with reinforcement. The system relies on a balance between shell production and shell degradation, a balance sensitive to subtle chemical shifts. When erosion outpaces deposition, vertical relief is lost. Reefs sink into sediments, reducing water flow and oxygen availability. Living oysters suffocate or are buried. Mortality increases, but without sufficient shell preservation, death no longer contributes to future structure. It becomes purely subtractive. This transforms death from a building process into a collapse mechanism. The unsettling part is how normal this looks while it is happening. From the surface, reefs still appear intact. Oysters still feed, reproduce, and settle. But below, the scaffold thins. The system becomes hollowed out, supported by fewer and fewer layers of preserved material. Eventually, a storm or strong current removes what remains. The reef does not fracture dramatically, it dissolves into the seabed. What was once a three-dimensional habitat becomes flat, biologically quiet terrain. No single death caused this. It was the cumulative failure of shells to persist long enough to support future life. Oyster reefs demonstrate a biological logic that feels backwards. Life here is not maintained by protecting individuals, but by converting their remains into infrastructure. When environmental chemistry interferes with that conversion, the system loses its ability to exist in three dimensions at all. The reef does not die because oysters stop living. It dies because their bodies stop lasting. The cleaner the water becomes, the more concentrated the contaminants inside the oyster. This is not a metaphor. It is a direct consequence of how filtration works at scale. Oysters remove particles from the water column and store what they cannot metabolize in their tissues. Nutrients pass through. Many toxins do not. Over time, this turns each individual into a localized archive of environmental exposure. The paradox deepens. The oyster's ecological value increases as it accumulates harm. Coastal waters with healthy oyster populations often show improved clarity and reduced nutrient overload. Phytoplankton densities drop, light reaches deeper, oxygen dynamics stabilize. At the same time, the oysters responsible for these improvements increasingly carry heavy metals, hydrocarbons, and persistent organic pollutants within their bodies. There is no effective detoxification pathway. These substances bind to proteins or become sequestered in tissues, remaining for the lifespan of the animal. From a survival perspective, this should be catastrophic. Chronic toxin accumulation is typically associated with reduced growth, impaired reproduction, and shortened lifespan. Oysters experience all of these effects. Yet populations can persist because the damage is distributed unevenly across time and individuals. Many oysters reproduce before toxin loads become lethal. Others die earlier, contributing shells to the reef. The system continues not because individuals are healthy, but because enough of them reach reproductive maturity before internal conditions become incompatible with life. This creates a troubling alignment between ecosystem service and individual sacrifice. The ocean benefits precisely because oysters are willing, biologically, to become sinks for contamination. They do not neutralize pollutants. They remove them from circulation and store them in living tissue. When oysters die, those substances do not vanish. Some remain trapped in shells and sediments. Others re-enter the system through decomposition. The cleaning effect is therefore temporary and spatially uneven. It works best when oysters are alive and filtering, and degrades when populations decline. This means the health of the water is tied to the continued survival of organisms already carrying increasing toxic loads. There is no reset mechanism. Each generation inherits an environment shaped by the accumulation of previous generations' exposure. In heavily impacted areas, oysters can reach a point where growth is stunted from early life stages. Shell formation slows. Immune responses weaken. Disease outbreaks become more frequent. Filtration continues even as internal systems fail. From the outside, the reef still functions until mortality accelerates. What makes this unsettling is the absence of intent or optimization. The oyster does not evolve toward a cleaner solution. It does not develop improved detoxification. It simply continues the same process until external conditions exceed what delayed failure can tolerate. The species improves its environment by absorbing the consequences of that improvement internally. It is a one-way exchange. The ocean offloads complexity and contamination into bodies that cannot refuse it. As long as oysters exist, this trade continues. When they disappear, the accumulated problems return to the system at once, no longer filtered, no longer sequestered. The improvement was never permanent. It was borrowed time, stored in flesh. For long stretches of time, oyster systems appear deceptively stable. Filtration continues. Reefs persist. Water remains clearer than it would be otherwise. The underlying processes do not signal how close they are to failure. This is because oysters do not respond to stress in ways that scale smoothly. They tolerate degradation until they cannot. The boundary between function and collapse is narrow, and it is often invisible. Physiologically, oysters operate near multiple limits simultaneously. Oxygen uptake depends on constant water flow, shell formation depends on carbonate chemistry, energy balance depends on slow, uninterrupted feeding. Disrupt any one of these for too long, and the system fails. Climate-driven warming increases metabolic demand while reducing oxygen availability. Acidification undermines shell integrity. Pollution adds internal toxic load. Each stressor alone may be survivable. Together they compress the margin for error to nearly zero. The unsettling part is that collapse is not gradual. There is no orderly shutdown. Once conditions cross a threshold, mass mortality can occur rapidly. Entire reefs can be lost within a single season. Filtration capacity drops abruptly. Water quality degrades. Sediments resuspend. Algal blooms intensify. The changes that oysters once moderated now accelerate in their absence. This is not a slow rebalancing. It is a phase shift. The system reorganizes around a new, less stable state. Recovery is difficult because the mechanisms that supported recovery are gone. Larval oysters require hard substrate to settle. Without intact shells, recruitment fails, predation increases, disease spreads more easily in degraded conditions. The feedback loops now favor absence rather than return. What makes this especially disturbing is how little disruption is required to trigger it. The system does not need catastrophe. It needs persistence of pressure. A few warmer summers, slightly more acidic water, marginally higher nutrient input. Each change nudges the system closer to a boundary that cannot be seen from within. Oysters do not know they are approaching it. They continue filtering, growing, reproducing, storing stress internally. When failure arrives, it appears sudden only because all the warning signs were microscopic, biochemical, and cumulative. From a human perspective, oysters are often framed as a luxury, a delicacy, an accessory to coastal culture. Biologically, they are something else entirely. They are overextended systems, performing ecosystem-scale labor with bodies that were never designed for buffering global change. They function without redundancy, without reserve, and without the ability to adapt quickly. The ocean relies on them anyway, not because they are strong, but because nothing else fills the same role at the same scale. Oysters matter because they demonstrate a rule that applies far beyond reefs. Some systems work not because they are safe, but because they have not yet reached the point where all accumulated stress becomes visible at once. When that moment arrives, the failure feels abrupt, even though it was built slowly, layer by layer, like the reef itself.